Alright, welcome. Today we are going to begin section 2 on electrical circuits. Our second unit in electricity. We're going to begin talking about electric circuits today and power. We're going to begin that by talking about series circuits. We have been doing a number of experiments in class over the last week where we've been talking about and examining series circuits. And today we're going to actually give them the official definition, talk about the results we've seen in the labs, talk about some of the math, and do a few practice problems so that we're prepared. This next week we'll then move into parallel circuits, then we'll talk more about how to analyze what's going on in the circuits. We'll talk about power, and then we'll also talk a little bit about home wiring, so maybe you get something practical you can use when you have your own home and you're a little bit older. Okay, so series circuits are electric circuits. That's a path for the electricity to flow. We talked about this. This is a special type of circuit where there's more than one resistor in a row, but there is only one path for the current to follow. So a couple of things here that are important to pay attention to. There's only one path, but there's multiple resistors or light bulbs or toasters or whatever it is, and they're all in a row and there's only one path. So a great example of this are Christmas lights. Old-time lights, they're better now. Christmas lights were wired where they were in series, so there was only one path for them to flow. So you'd have the outlet plug, and then there'd be wires. One wire would come out and it would go to each little bulb. In a row. And then that wire would go back around to the other end of the outlet. So if you unplugged it, they all went off. But if one of these light bulbs burnt out and the filament went bad, then no current would flow. So because there was only one path, any bulb going out turns out all the bulbs. So one bad bulb equals no current. So anytime I open a switch or I unplug it, it turns off the current. Anytime anything breaks, it turns off the current. So a lot of times your house will have a combination of series and parallel circuits. We'll talk about parallels later, but so like for example in the classroom, if I flip the light switch, the lights turn on. So the lights are in series with the light switch. If current's not flowing through the switch, then current won't flow through the lights. So let's talk about how resistance combines. So resistance in a series circuit. So like water in a hose, we've talked about water in pipes. If I have water in a pipe and then I pinch the pipe off, that's going to slow down how fast the water can move throughout the pipe. And if I pinch it off again, then I'm going to slow down that water even more. So resistors in series each have a part and each have a role in slowing things down. And series circuits are really nice because the total resistance, the resistance of the whole circuit, is just the individual resistances added together. So if I have three different resistors, resistor 1, resistor 2, and resistor 3, the resistance adds up. And that goes with some things that we saw in the lab. What we saw in the lab was that the voltage of the whole circuit, the total voltage across all three light bulbs, equaled the voltage across each individual light bulb. Right, the battery's voltage equaled the voltage across each one. In the lab we saw the 3 volts from the battery equaled the voltage drop across each individual light bulb. Well, so if these all add up, I can also say this. Since Ohm's law is voltage equals current times resistance, I can substitute IR in for my different voltages. So IR total equals IR1 plus, that's voltage 1, plus IR2, which is voltage number 2, plus IR3. And again, I times R is the same as voltage, so we're not doing anything here, we're just substituting. But because I have I in every single term, those I's cancel out. Right? I is in every term in the equation, so they all just cancel out. I can divide both sides of this equation by I and get rid of all my I's, and that equation is going to simplify back to R total equals R1 plus R2 plus R3. So our resistance combines like we would expect it to, and it matches with the math from Ohm's law, and it matches with the experiment. So what about this voltage thing? So we saw this in the lab, voltage in a series circuit. We saw that as you went around, we had 2 batteries connected, and then we had 3 light bulbs, and I'm just going to draw them as resistors just for simplicity's sake. Doesn't really matter. But we had 3 things that would take away energy. We talked about it in class a little bit, but the voltage here between these two batteries was 3 volts. And that was an increase in voltage. Here it was 1 volt, 1 volt, and 1 volt. And these were all decreases, or voltage drops. And voltage drop is when energy is taken from the circuit. So a voltage drop is that change in voltage that we see here. Here, basically, we started out, if we were to graph what's going on, right here, I'm going to graph this right inside, and I'm going to do voltage right here. And this is 3. Here, we'll put 3 at the top. 3, 2, 1, 0. So when we come across, and before we hit this first bulb, our voltage is at 3. We go across this bulb, and it drops down to 2. Then we hit this bulb, and we lose another volt, so it drops down to 1. And then when we get to the third light bulb, it takes away a volt, and we drop back down to 0. And when we come back around and reconnect with the battery lifts it all back up and gives those electrons that energy again. So remember, that's what a battery does. A battery gives energy to the electrons. Alright, I think that's a good spot to stop. We will get into parallel circuits more next time. And until then, have a good day.